to continue the discussion on enzymes and do a brief summary of the kinetics and regulation. And then on our next lecture, we're going to talk about inhibition patterns of enzymes with their inhibitors around. So today, we're going to finish up all of our enzyme kinetics. So the first part will be enzyme kinetics and regulation. So we need to learn a few more definitions, building on what we did last time. So we need to learn what the word kinetics means. Okay? And all it means is a mathematical way of describing what's happening, and the enzymes are the catalysts of these reactions. So we can measure a few things about these reactions. We'd like to know how rapidly they're proceeding. And remember from last time, when I say how fast or rapid it's proceeding, I don't mean the individual bonds breaking and electrons moving. I mean how frequent this entire reaction is taking place. Okay? So we can measure the rates at which that's happening. We can also talk about the mechanism in which it happens. And the mechanism is just like you did in organic, it's a step-by-step description at the molecular level of how things are moving, what's attacking something else, which lone pair is moving where protons are going, and so forth. So we can talk about the rates of these reactions, which we'll measure using certain either spectra or other methods, which we won't talk too much about. Or we can talk about an enzyme's mechanism, and we derive the mechanism from how we observe the rate changes. Okay? So the first thing I want to talk about, though, is ignore enzymes for a second and just talk about simple chemical reactions. Okay? So a basic chemical reaction, very simple. We turn a substrate A into a product P, and sometimes you call the substrate a reactant, which is perfectly fine. We turn A into P, and that occurs under certain conditions, whatever they might be. Okay? An example of this could be gasoline exploding, right? So gasoline combusting with oxygen to make the products CO2 and water, right? So a simple chemical reaction. Could I measure the rate of that reaction? Yeah, I've got a couple options on how I could measure it. I could observe the amount of CO2 and water, or CO2 or water, either one, produced. And if I had some way of measuring that, I could measure the change in that product over time. So that's shown here as a delta product concentration over a change or a delta in time, right here. Right? So a change in product over time. But equally valid would be the measurement of the disappearance of the substrate or the disappearance of the reactant, like gasoline. So I can measure the appearance of the product over time, or the disappearance of the reactant over time, and of course the negative of that would be equivalent to the change in product over time, assuming it's a one-to-one stoichiometry. And so here we'll pretend it's a one-to-one, right? So we'll have one molecule A, or 1 mole of A, turning into 1 mole of P. And the rate at which that occurs would be the appearance of P's concentration over time, or the increase in the concentration of P over time, or the decrease in the amount of A over time. Those numbers should agree with one another. Okay? We'll call the rate at which this occurs, the change in concentration over time, the velocity. So we'll write V equals to the change in product over time. Right? And so we can draw a graph based on that, the rate that the product is being formed compared to the amount of initial starting material, the concentration of A, concentration of our reactant. And if I begin with more reactant, the rate at which product is formed is faster. And if I keep measuring that at many different reactant concentrations, and I plot them, the rate versus those concentrations, I get the graph you see in the center of the screen here. So each one of those points represents one of those experiments, and I get a linear relationship. So the more reactant I start with, the faster it turns it into product. A thimble versus a fuel versus, or a thimble of fuel versus a barrel of fuel versus a warehouse of fuel, right? They're both going to explode, all three will explode in a relatively short amount of time, but the more fuel I have to start with, the more violent, the faster the reaction proceeds. Okay? That's the idea we're going to get across here. Simple chemical reaction. If I add more fuel or add more reactant, it reacts faster. There's no limit to this, right? Except for the physical limitation of, say, molecules moving in space and time. But the bigger the reactant, the faster it will, so the bigger the concentration of reactant, the faster this reaction will take place. Okay? So I can write that in an equation that the rate it occurs, V, is proportional to the concentration of A. Right? So V would equal some number times A. Right? It's proportional to it. I don't know what that proportionality is, but V is proportional to A, the concentration of A, for a simple chemical reaction. So what's the proportionality constant? We're going to call it K. K for constant, because it starts with K in German. So the rate constant K will be the number I need to multiply times the concentration of A to get V. So if you want to write it as an equation, you could simply write V equals K times the concentration of A. Okay, so that's what I'm saying here. The change in product over time is the velocity. The velocity can also be expressed as some constant of proportionality, the rate constant, right, times the concentration of substrate that I start with. And we know those are proportional to each other because I got a straight line, K being the slope of that line. Okay? So now let's do some unit analysis here. So the product over here, right, is going to be in some concentration. You could be in millimolar, parts per million, parts per billion, donkeys per field, whatever it might be, right? It's a concentration, right? And the units of time, of course, would be some unit of elapsed time, like seconds or hours or centuries or whatever it might be. And the ratio of those two is velocity. So this is a concentration divided by a time. Well, on the right-hand side of this equation, I know I have a concentration of A, and A is in whatever units P was in. It's, millimolar, parts per million, parts per billion, whatever it might be. So if this is in, let's say, millimolar, and V is in millimolar per unit time, or millimolar per second, for example, then K must have the units to make these two have the equal units. It must be per second, because the velocity is in units of concentration over time. A is in units of concentration, so K must be in units of per time, or inverse seconds, or hertz. Okay, so here K is representing the proportionality constant, the rate constant, and its units would be per second, or seconds to the -1 is a way to write it. And this is considered a first order reaction, because the rate is dependent on the concentration of one of the substrates raised to the first power. The 1 is understood. So the power of this A is 1. Right, so it's called a first order reaction. The rate is dependent on the concentration of one thing, and that thing once to the power of 1. Very simple first order reaction. Okay. Let's consider a second order reaction. What would that mean? That would mean the rate is dependent on the concentration of two things, perhaps. So one example of that would be this reaction down here. We're still talking about simple chemical reactions, no enzymes yet. Right? So we have two reactants, A and B. They interact and form products, C and D perhaps. We're not really concerned about the products. Right? What is the rate of this reaction? Well, we can measure it as the change in concentration of C over time. We could measure it as the disappearance of B over time, the appearance of D, the disappearance of A. We've got lots of options. Right? But on the right-hand side of that equation, the velocity would be equal to some rate constant, K. We'll just call it K. It's not necessarily the same K in every reaction, but we'll just write K there, times the concentration of the reactants. So concentration of A times the concentration of B. So clearly this velocity is dependent on two things, each raised to the first power. So if I count the number of things it's dependent on, it's 2. So this is second order. Right? Another example of second order, not shown on the screen here, what if I had A turning into P again, like on the last slide, but the ratios weren't 1-to-1. It wasn't a 1-to-1 stoichiometry. It takes 2 A's to make it 1 P. So it's a 2-to-1 molar ratio. That would be a second order reaction. Because if you wrote the rate constant for that, the equation for it, it would read V equals some constant K times the concentration of A times the concentration of A again. Because 2 A's making P would be like saying A plus A, or A squared. So it would be dependent on the concentration of A squared if it were 2-to-1 ratio. That's again second order because it depends on something being there twice. Okay? So if I make up one here, that's this reaction here, A plus B forming some products, and the stoichiometries are one A and two Bs, that would not be second order. What do you think it would be? If it were one A and two Bs need to react to form some products. What order would that be? Say again?
Third order.
Third order, right. Because the rate equation would read V equals some rate constant K times the concentration of A times the concentration of B squared. Because B represented twice. I need two of them to interact. So you just count up the number of things, the number of reactants you need, including taking notice of their coefficients. So that would be third order. Let's look at the units real quick. We said the units of K for the first order at the top were simply per second, because the units on each side of an equation must match. So here we had velocity as a concentration over time, and this was concentration, so we needed an over time, right, as K. For a second order rate reaction here, the velocity is still, I'm measuring either C or D, one of them, not both, per unit time. So V is still concentration over time. That's not going to change. But now I have two concentrations on the right. So the units of K are not necessarily just per second anymore. It's per second per molar, because the units on each side must match. Right? If you had a third order equation, it would read molar to the minus 2, S to the minus 1, because I have to cancel out everything except the moles per second. Right, everybody get how to do these? Just count them up, and the units must match. Okay. So let me tell you another story real quick. It's not exactly the same. Let's say you have a reaction again of A and B forming some products. Maybe it's C, maybe it's C and D, or maybe it's 7 products. It doesn't really matter how many products there are. We're having a reaction start with A and B, and it's making some products. Or we can write our equation again. It's V equals some constant times A times B. But let's say B is water, for instance, or oxygen from the atmosphere, or something exceedingly abundant that you really don't measure its concentration. It's just always there. And as the reaction proceeds, the concentration of B never really goes down significantly because there's just so much of it. It's like doing a reaction in water where the thing is reacting with the water. You're really not going to change the concentration of the solution by adding 1 or 2 or 3 water molecules or removing them. So essentially B doesn't change. So the reaction becomes independent of B, becomes zero order with respect to that reactant. Okay, so we can rewrite our equation as V equals K times A again, because it does depend on A, but B to the 0, because it really doesn't depend on B anymore. B is virtually omnipresent. It's always there. You can't make it go away. So we can eliminate that. B to the 0 becomes 1, and it goes away. So we rewrite the equation as K prime. It's just like saying K, it's just our new K, right, times A to the power of 1 again. So now V is clearly dependent on only one thing, and it looks first order. But we know it truly isn't first order because the B must be present. So we call it pseudo first order, right? Every time we get rid of something, we know it's had to be there for the reaction to take place, but it's always there. We can't get rid of it. It's part of the natural environment, right? It's like trying to remove oxygen from the air when you're doing a combustion reaction. You really can't unless you isolate it in a chamber that doesn't have oxygen. If you're just doing it out in the open, there's going to be oxygen around, and it's not going to be truly depleted in any way, right? Or if you're doing it in the middle of a lake, right, a reaction that involves the water of the lake, you're not going to deplete the lake in any appreciable amount. And so we call this pseudo first order. I give you another example, and you tell me what it would be. If my reaction were the one I said just a minute ago, 1A and 2Bs interact to make some products, and A is omnipresent. It's virtually impossible to not have it around. A might be oxygen, for instance. So I have 1A reacting with 2Bs to make products. I can write the rate equation as V equals K times A times B squared, right, because there were 2Bs. But A, we said, was virtually omnipotent, right, or omnipresent. It's always there. So we can write the A to the 0, and it kind of goes away. because you can't get rid of it. So if we lose the A in the equation, it becomes K prime times B, still squared. Right? So it's no longer a third order, like you said. It would be what?
Pseudo second order?
Exactly. It's pseudo second order. It is the new order. You still count up the things that remain. In the example on the screen, it would be pseudo first order. In the example I just spoke, it would be pseudo second order. Whatever one's abundant, you get rid of it. Right? It's not always subtracting it by 1, but let's turn that around and do the one I just said again a different way. What if it's A plus 2B makes products, and this time B is the one that's always present? What would the order be? So I'll repeat it. It's A plus 2B react and make products. And B is the thing that's almost always present, where you can't get rid of it. It's virtually unlimited. What would the pseudo order look like? It's normally third order. What would it be now?
Would it be pseudo first order?
It would be, because the only thing left would be A, like the one on the screen here. Because the B, even though it's squared, is going to 0. I don't count it anymore. You can't diminish it in any way. Okay, so whatever one's the abundant, always present thing is the thing that goes away, however many of them there were. And whatever's left, count the order. Count the number of concentrations of things that remain. Okay, let's move on to, that's just simple chemical reactions. Let's do this in the presence of an enzyme and see what changes. Well, we have to make some assumptions first. When I do a reaction that requires the presence of an enzyme for it to occur at any appreciable rate, right? Remember, some of them are exceedingly infrequent, right? So with the enzyme present, it occurs often, and we're going to hold the amount of hold the amount of substrate constant. So it's a bucket of whatever the substrate is. We're going to hold it constant. And if I add more enzyme to that solution, it tends to go faster. Right? And that should make sense. If I have so let's say I have a barrel of pieces of paper, and you as students are sitting around with your little safety scissors, right? You dive into the barrel and ask you to cut up this paper for me. Every piece of paper needs to be cut in half. Grab some little strips of paper and cut them. There's a room full of students with scissors doing this. If I fill the room with more students, you're going to go through that bucket faster. Right? I haven't changed the amount of strips of paper in the bucket at all. But if I add more enzyme, you doing the work, right? You're not consumed in the process. You can cut paper more than once. Right? But I add more of you to the room, you're going to go through the bucket faster. The rate at which you accomplish your goal of cutting the paper will be faster. And there's truly no limit to that, up to the point of I can't fit any more people physically in the room, right? So the more enzyme I add, which on this graph here is on the x-axis, the faster the rate will go for a fixed concentration of substrate, for a fixed number of papers in the bucket. Now, if I start changing that, that's a different story. We'll talk about that one next. But holding S constant, if I add more E, it goes faster. Okay? So if I think about it, it's really pseudo first order, right? It's not really dependent on the amount of S I have anymore under those conditions, right? If you never can run out of stuff in the bucket, it's an endless bucket. The more students I had to cut the paper, the faster it will go. So this is linear forever. Okay? So this looks like a pseudo first order reaction because the amount of substrate that's there really doesn't matter as long as it's a lot. We call it saturating or infinite amount. Okay? Let's turn the argument around the other way. What if I had a large amount of enzyme present but limiting amounts of substrate? And we're going to focus our discussion on that for the rest of the talk. Right? Let's say the amount of enzyme is fixed, because we know if we add more, it will go faster. That's what this graph tells us. So from here on in the discussion, we're going to hold the amount of enzyme constant, not change it. And see what happens to the velocity if I change the amount of S. Not infinite amount anymore, but sub-infinite amounts. We'll see what happens. Okay? So here's the scenario here. I have a certain amount of enzyme present, and I add the substrate to the solution. The first thing that the substrate, or reactant if you want to call it that, has to do is physically bind to the enzyme. We talked about that in our last lecture. There's no action at a distance. It doesn't send it a text and say turn into product. They physically must make contact. Okay, so we write that in a graphic form here as E plus S, enzyme plus substrate, and the arrow here going to the right, forming an ES complex. We're going to call that the enzyme substrate complex. It's just the substrate bound to the enzyme at an active site. Right? So that's where substrates bind, at the active site. No chemistry has taken place yet, it just binds. This could be an induced fit, this could be a lock and key. There's lots of ways you can do this, but it must make contact. Okay? At this point, ES can do one of two things. The simplest thing ES can do is simply let the substrate go. And it goes back to being E plus S. They're separate from each other. So it binds in the active site, and the simplest thing this ES complex can do is just let the substrate go. And that happens a lot, right? So many times enzymes bind molecules that are not the right substrate, and it's very prone to just letting it go. It doesn't bind very well. Even if it's the correct substrate, it lets it go many, many times. The other thing the ES complex could do, right, is get it over the transition state. Instead of falling back to E plus S, it could fall forward and become EP, the EP complex. And then, of course, EP would let the product go and become E plus P. That's all shown in this step here. ES becoming E plus P. So this first arrow is simply the bind and release step, right? And the second set of arrows shows the catalytic step, the turning it into product and letting the product go as one common step here. But the product, since the enzyme is reversible, could rebind to the enzyme and turn back into the substrate. So that's totally reversible as well. So these are the four verbs or things that could happen, right? So enzyme binding substrate, that's here. That occurs at a certain rate. We could have put a rate constant on this arrow, right? Call it K1 or K formation or K dog or whatever you want to call it, some rate constant. It could fall apart. We generally call that K minus 1. It's not a negative number, it's just the subscripts to indicate it's the opposite process of this one. So if you call this one K dog, you call this one K cat, right? That's a terrible way to do it because K cat means something else. But, so we're going to call it K1 and K minus 1. ES, turning into E plus P, is kind of the step that makes product. So we could call it KP for product. We could call it K2 because we already used 1. And the arrow underneath could be K minus 2, right, as a subscript, or K parrot, or K giraffe, or whatever subscript you like to call it. But as long as it represents the opposite process. Okay, so that's all these things mean. But if I have a very large amount of substrate around, right, let's say an infinite amount, right, won't every enzyme have a substrate bound to it? Because the rate at the forward reaction here would far exceed the reverse rate. E plus S forming ES would occur all the time because you have an infinite amount of S. But ES falling apart into E plus S would occur, but the moment it does, there's an infinite pool of substrate around to rebind the enzyme. So under those conditions, there will be no free enzyme. It'll all be in the ES form. And thus it becomes independent. This reaction only depends on the concentration of one thing, the ES complex, which effectively is just the amount of enzyme you have in solution, because every enzyme will have a substrate bound to it. This is exactly what we said a minute ago. If you have saturating amounts of S and a fixed amount of enzyme, it becomes pseudo first order. It's only dependent on one thing, the concentration of the ES complex. Under these conditions, that's just the amount of enzyme you have. That's why we call it pseudo first order. Okay. So let's throw some numbers on there. Here's the ones I just described. We'll call the forward reaction K1, reverse K minus 1, the formation of product and release of product K2, and the rate of this going backwards K minus 2. Yes, I drew the arrow a little smaller. We'll get to that in a second. Okay. If I plot this on the graph at the top, we're not talking about infinite substrate anymore. We're going to hold the amount of enzyme fixed and vary the amount of substrate. So that's on the x-axis here. So this is substrate concentration for a fixed amount of enzyme. And what happens to the rate? Well, everywhere on this graph, if I add more substrate, pick any point and look at a point to its right, the velocity will always be faster. So if you pick any point on this graph and get the velocity, right? Pick any point with a higher substrate concentration and get the velocity, it will always be a faster velocity. But this is not a linear relationship. You notice this curve tends to approximate or curve over and reach this asymptote up here. Okay? We saw something like this before. As we increase the substrate concentration, no matter what, the velocity always increases, but you're getting diminishing returns. As I start increasing this towards infinity, this increase becomes smaller and smaller and smaller. It's still going up, but the increase becomes extremely small, and if I ever could reach infinity, or saturating amounts of substrate, the reaction will go as fast as it possibly can go. Okay? We'll call that the maximal possible velocity, or Vmax. Okay? It's the amount of rate of conversion of substrate to product I can achieve given an infinite amount of substrate and a fixed amount of enzyme. Could I make Vmax larger? Not by adding more substrate. But I could make it go faster simply by adding more enzyme. So Vmax is proportional to the amount of enzyme I have. Right? We already said that a couple slides ago. It could go faster if I add more enzyme. Here we're going to talk about a fixed amount of enzyme, and that's going to give me a certain Vmax. Okay? We have a problem with this analysis though. So here, this whole thing is completely reversible. E plus S forming ES, ES falling apart into E plus S, ES turning into product and releasing it, and the product rebinding, reversing the chemical step, and becoming ES again. I'd like to measure the forward reaction only. So if I could only get this thing to not go backwards, can I find a way to do that? Well, if K minus 2, the rate of this going backwards, were 0, right? In other words, an irreversible reaction, that would be wonderful. But not all reactions are irreversible. Some of them have a significant number for K minus 2. It's not 0. But if I start the reaction with a bias, where in the bucket, or in the tube, or in the flask, or whatever you're using, there's no product to start with, right? The concentration of P is 0. I don't put any in there. The only thing in there is substrate at a certain concentration, whatever it might be. And then I add enzyme and mix it. Well, initially, in the very first instance, there is no product to go backwards. So the rate of K minus 2 is 0. There's no way it can go backwards if there's no product present. And we want it to go at a certain rate, so we add less enzyme, make it go slowly, so that the product doesn't accumulate in the first, say, few minutes. Right? If we add more enzyme, yes, we'll get more product more quickly. So we add less enzyme so it goes slowly, and we measure the rate at which S turns into P. We can do it with a spectrophotometer, you can do it with a radioactivity, with a Geiger counter, you can do it all sorts of ways. You just want to measure the conversion of substrate to product, like we said on the first slides. But if I add more substrate to begin with, it should go faster. And if I add more substrate, again, faster. And I can start plotting it as different points on the x-axis here and getting points on the y-axis, and I'll generate this curve. Okay? But I had to bias it so that K minus 2 is essentially 0. And I said I want it going backwards. Okay? So we'll do that on this graph. So here I'm measuring the product. Look at the y-axis, product, over time for varying amounts of substrate. Okay? You notice it starts off really slow. If I add more substrate, it goes up faster, faster, and faster. And I'm doing this at the very beginning. We're going to call it V naught, right? I'm biasing it. So I'm doing it at the beginning of a reaction. I don't let this go on too long, right? I don't measure it for too long. But the K minus 2 term, we're going to say is 0. We make it disappear by initializing this condition. Okay? Only looking at it at the initial rate. Okay? So what if I keep adding more substrate? I'll eventually reach the same equilibrium because that's determined by the amount of substrate that was initially present and the amount of product I make from it. They'll all come to the same equilibrium, right? Because we don't change delta G. Remember, enzymes do not change delta G. But the rate at which we approach the equilibrium is faster as I add more substrate. And at some point, I can't add any more substrate. It's saturating, and that's what this V naught represents here, right? It's as fast as it possibly can go for that amount of substrate. If I keep adding more and more, this line gets faster and steeper, but it'll never get vertical because it can't go infinitely fast. Can someone think of why it can't go infinitely fast? Even if I throw an infinite amount of substrate at it, it can't go any faster than a certain number.
Doesn't it just have to do with sort of physics, like how quickly things bump into each other?
Right. So unlike a chemical reaction, the reaction only takes place in the active site here. So the substrate must bind to the enzyme. The chemistry step must happen, which takes a small amount of time. It's very, very fast for some enzymes, but it takes a small amount of finite time. And then you have to release the product. There's a delay before the next substrate finds its way into the active site. We do the chemistry step again. We release the product. There's another delay. The substrate finds its way in the active site. This repeats over and over and over. The only part of that time frame I just described that I can shorten is the delay between releasing one product and binding the next substrate. If I add more substrate, the chance of it finding a substrate goes up drastically, right? So I diminish that delay. That delay can at most go to 0. But the chemistry step still takes time. You can't change that with an enzyme or by adding more substrate. You can change it by changing the temperature or pH or something like that, but we're holding everything else constant. So for the certain fixed conditions, I can add all the S I want, but it can only go so fast. We called that Vmax. Okay? So if I look at this and measure the initial velocity here, this is product versus time on this graph, and I measure the initial slope, so S1, the amount of substrate, would be a rather shallow line here. S2 is faster, S3, S4, S5 is probably going to be faster than that, but it won't go vertical. Right? It'll get steeper and steeper, but it'll never get vertical. And if I plot all those lines, these V's, versus the amount of S, I'll get this graph. Okay? The bottom right graph here. Okay, again, we're going to get rid of this K minus 2 term because we're going to bias it such that the conditions don't have any product around when we start. So in the graph on the bottom right, if I plot all those substrate concentrations, remember this is a new x-axis. This x-axis represents all those substrates, S1, S2, S3, S4, from the previous experiments. That's what all these little dots represent. And they all gave me a certain line, a certain angle, a certain velocity, and I'm plotting those on this graph, and you notice it gives me this curve. And as I add more substrate, the best this can do is reach the asymptote of Vmax. Right? You can't go faster than that. So no matter how much substrate I add, it can never go completely infinitely fast. And so I get this shape. Right? Anybody remember what this shape is called from high school geometry? It's not a parabola. It's a what? Where you have a line approaching an asymptote. What do you call that? You guys remember from geometry, it's called a hyperbola. And when it does so on the axes, like x and y axes, it's called a rectangular hyperbola. It's approaching one of the horizontal or vertical lines. So it's a rectangular hyperbola. We'll remember that in a little while when we talk about it. Okay? So what this indicates is as I saturate the solution, S approaching infinity, right, then the velocity doesn't approach infinity, it approaches a maximum called Vmax, the maximal velocity. Okay? And we can write an equation for this. It's not a straight line, so this is not a y equals mx plus b type equation. And the equation is written here in the middle of the screen. It's called the Michaelis-Menten equation. And it means that the velocity, the initial velocity, that's why it says v naught, right? So we're biasing those conditions to get rid of that k minus 2. The initial velocity is equal to the maximal velocity times the substrate concentration divided by the Km, which is called the Michaelis constant, named after the same person, plus the substrate concentration. Okay? And if you look at this equation, there are two variables in this equation, right? One is the independent variable on the x-axis here, S. It occurs twice in the equation. And one is the dependent variable, or our answer, V naught. It occurs once. These two terms, Vmax and Km, are constants. Vmax is the fastest it could go, given that S is infinity. And Km is a measure of how tightly this substrate binds to its enzyme. Right? It's an inverse relationship, but Km measures how tightly the interaction is, or how tight the interaction is. We'll talk about it in just a minute. But Km, if you want to calculate it, it's the rate at which the E and S can fall apart, right? So looking at the top up here, rewrote our equation, losing the k minus 2 because we're biasing it. So how many ways can ES fall apart? Well, it could just simply become E plus S, or it can turn into product and release the product. So there's 2 ways it can fall apart. And how many ways can ES be formed? Since we are biasing that this can't happen, there's only one way we can make it, and that's E binding to S to make ES. The rate of it falling apart is a K2 and a K minus 1, and the rate of it forming is just K1. So it's the ratio of falling apart over formation. So it's a dissociation constant. It's the rate at which something falls apart or breaks down or comes apart compared to the rate at which it was put together. Right? So we always tend to measure things as dissociation constants. So you can imagine if E plus S, if they like each other, if they have a high affinity for one another, I expect K1 to be a large number, right? Because they will bind each other very well. I expect K minus 1 to be a relatively small number because they like each other. They don't fall apart readily, right? So K1 will be much larger than K minus 1. That means the numerator, no matter what K2 really is going to be much larger than K minus 1 because generally K1 and K minus 1 are faster than K2.
I have a quick question.
Uh-huh.
On the slides that I printed out, it has 2 different equations at the bottom, and I was just wondering, at the end of the equation, it was divided by K1 plus K minus 2. Is that right, or should I just look at the one you have on the screen?
When you print these, it's got an animation in it, so you don't see the print. So what you're seeing is this equation?
Yes.
And
okay.
Remember we said we're biasing this. This is the true equation, but we're biasing this such that we measure it only at the very beginning of the reaction. So K minus 2 is effectively 0. So we can lose it in the progress of calculating this. So that's why it appears that's the other equation.
Thank you.
Right. When you print the slide, it generally prints both, everything that could be there. Okay. So I was saying if we have a large K1, all right, here, and a very small K minus 1, this number, K1, is large, and K minus 1 is small, so the numerator will be smaller than the denominator. Right? That makes K1 small. So if they have a high affinity for each other, Km is a small number. If they have a very weak affinity for each other, let's say they don't like each other, it doesn't fit well, it's a terrible substrate for this enzyme, then K1 is not going to be very big. They don't associate readily. And K minus 1 is going to be a large number because if they do happen to bind to one another, they fall apart readily because it's the wrong substrate or it's a poor substrate. In that case, the numerator will be large compared to the denominator, and Km will be large. So it appears that Km has a reciprocal relationship with affinity, and that's true. Right? So a large affinity, right, high affinity for one another, means a low Km value. And a large Km value means a weak affinity of E and S. Okay, so I want to disabuse you of a major misconception here that students do. If you look at the graph on the right, if I look at substrate concentration, this axis is a measure of substrate concentration. It has units of concentration, millimolar, parts per million, whatever it might be, but it's a unit of concentration. Km is on that axis. It's this point right here. So Km has units of concentration. Whatever S is in, that's what Km is in. Okay. The other thing I want to point out is the y-axis. This has units of velocity, concentration per unit time, right? And Vmax is on that axis. It's on the y-axis. I know this line's got a line to it saying Vmax, but it means this y value is what this line is approaching. Right? It's approaching this y value like that. Never quite gets there until you get to infinity. But this has units of concentration over time. So the x-axis and y-axis units are not the same. So there is no way a value on the x-axis could be equal to any value on the y-axis. They don't have the same units, right? So when I ask you to define Km here, it looks like it's the amount of concentration, right, that point right there, that's required to achieve a certain velocity. So find this point where we hit the line, and that's a certain velocity. Okay? That does not mean Km is equal to this velocity at all. No more than this point says this concentration is equal to this velocity. They're not equal to each other at all. Km is the amount of S required for this equation to be satisfied to give me this V. That's what that means. Okay? So this point halfway between 0 and Vmax would be Vmax over 2, or half the maximal velocity. In order to achieve that, I need a substrate concentration equal to this number, according to these dotted lines, right? That's what Km represents. And I want you to prove that to yourself with a little mathematical problem solving here. It's three simple exercises I want you to do on your own, right? I want you to do 2 limits and 1 plug-in, right? I'm just going to describe them, and if you want, you can pause it and do it on your own, but I want you to do these and prove it to yourself. What would the velocity be? What's the limit as S approaches infinity? So S gets very, very larger. This does not mean plug in infinity for S. That's not what limits mean. I want you to find the limit of this as S approaches infinity, right? And you should confirm that it is Vmax. Okay, so try that. Remember, go back and look up how to do limits. Also, find the limit of the velocity as S approaches 0. That does not mean plug in 0 for S. I mean as S gets exceedingly small from the positive side. So if S is getting really, really small, what is the velocity? Right? And you should come out to, it turns out it's the velocity is at that limit is Vmax over Km. Okay? And I also want you to tell me what is the velocity, this one you can't plug in because it's not a limit. What is the velocity when S equals Km at this point here? And you should get Vmax over 2. That's what the velocity will be. But that doesn't mean Km is equal to that. So don't make that mistake. And I promise you'll see it on the test. It's occurred on every single exam I've given in this class since I started teaching it back in, 8 years ago or something. So 21 times I've asked this question. Choice A, well, let me read the question to you. It always says, what is Km? Or Km is equal to what? And choice A always says Vmax over 2, or 1/2 Vmax. And without fail, a third of the class will pick that answer. And I'm telling you it's wrong. Don't pick it. A third of you will still pick it. Okay? Km is not equal to 1/2 Vmax. Km is equal to the amount of substrate it takes for the velocity to be equal to 1/2 Vmax. That's the right answer. Don't tell me that they're equal to each other. Okay? So let's talk about Km a little more. So every point on this graph represents some substrate concentration and its corresponding velocity given by the Michaelis-Menten equation. Okay? As S approaches infinity, the velocity becomes independent of S. Remember, it's always abundant now. So if S approaches infinity, it should approach 0 order. It's not dependent on anything anymore. If something is 0 order, it's a constant. And I get Vmax. That makes sense. Right? As S approaches 0, it becomes first order with respect to S. And you'll see that's why it's still dependent on a number. Okay? As S equals Km, I get a single number. It's not a limit anymore. So when S equals Km, like I said there, so S here equaling Km, the velocity, or V naught, equals 1/2 of Vmax, or Vmax over 2. Okay? This does not mean that they're equal to each other. Don't tell me that. It's not true. Okay, so here on this graph, one more time, same graph, S on the x-axis, V naught, or velocity on the y-axis. To achieve 1/2 maximal velocity, I need this amount of substrate. Okay? Does that mean if I take the Km value, the amount of substrate is a Km, and double it, do I get doubling of the velocity? Of course not. This is not a linear association. If it were linear, then that would be true. That's a linear relationship. You double A, or double X, you double Y. That's linear. This is not, right? It's hyperbolic, so you can't multiply one and expect the other to be multiplied by that. Right? So looking back, if you double S here, that doesn't necessarily double V. And you have to go through this calculation. So if I double the Km, double the substrate concentration, I'm only going to get just a little bit more velocity. It doesn't double the velocity, so don't tell me that. If it did, this would be a linear relationship in a straight line. It's not. Okay? But what does this mean? What if Km, the real Km value, weren't where it is on this graph, it was way out here, so farther down, higher concentration. Then this curve, this pink curve you see here, wouldn't go through this point. If the Km were here, then it would go through this point, because that would be where 1/2 Vmax would be. So it'd be a lazier curve. It would still reach the same Vmax, it would just get there a little more lazily. If Km were a smaller value, right, so say down here, somewhere at this point, right? I know you can't see my mouse, you guys listening live, but you'll see it on the video. If Km were a smaller value, then the pink line would go through this point. So it'd be a sharper rise, but approaching the same asymptote. And that goes in line with our interpretation of Km, right? It's the amount of substrate it takes to achieve a certain velocity. If it takes much more substrate to achieve that velocity, I must really have to throw the substrate at the enzyme to get it to work, because it's taking a lot more to get it to go a certain pace. So it must not be binding very well. Large Km, not binding very well. If the Km is very small, then it doesn't take a lot of substrate to get it to go fairly fast. It must hold on to what it grabs. So a low Km value, very little amount needed to get this thing going. So it must bind tightly. So that's exactly what we just said. That's the interpretation. The lower the Km, the tighter the binding. Well, I can use this as a tool. I can measure the Km in a laboratory setting, and the reciprocal of that will tell me the affinity of E for S. Is this a tightly binding ES or E enzyme to substrate relationship? So I have some definitions, there's an interpretation of it, and I can use it as a tool. It's a measure of binding affinity with an inverse relationship or reciprocal relationship. Okay, so be careful what question I'm asking you here and how you answer it. Okay. So we'll do a little bit more math here. This slide might look a little different than the one you guys have downloaded if you downloaded it before today, because I updated it today. I wanted to put this in there for you. So the traditional way to look at this is, if you look at these curves, they're not straight lines. Well, we like straight lines, right? What's the beauty of a straight line? I know the equation of a straight line. It's very easy. You learned it back in grade school, right? It's y equals mx plus b. How many numbers does it take to describe a straight line? Everything about it. If I know m and b, the slope and the y-intercept, I know everything about that line. This one's a little more complicated, right? I don't like curves. I'd rather just have a simple straight line. So a couple of researchers, Lineweaver and Burk, saw this equation. This is the Michaelis-Menten equation. So Lineweaver and Burk, it's a professor and his graduate student, were looking at it, and they said, well, that curve that Michaelis-Menten plotted, it's a rectangular hyperbola, right? And they remembered back for their high school geometry that a rectangular hyperbola has an equation of y equals 1 over x, right? It's a reciprocal equation, right? Sometimes it's y equals minus 1 over x. We'll ignore the minus sign. It's still a rectangular hyperbola. It's just reflected about the axis. So they said if it's a rectangular hyperbola in the equation, y equals a reciprocal of x, if I flip it over, I'll get 1 over y is equal to x. So 1 over y will be proportional to x. That's a straight line. My axes are going to look very odd, right? It won't be a y-axis anymore. It'll be a 1 over y-axis and a 1 over x-axis. But I'll get a straight line, right? And so what would happen to the equation over here? So they had an idea to make it a straight line, and they got a Nobel Prize for this. So if you paid attention in high school geometry, and you can do a little algebra, you get a Nobel Prize. Right, so I'm waiting for you guys to get yours later when you apply some simple things you learned to a more complex subject, and you'll get one too. So let's see if you can do what they did. Look on the right here, we have the Michaelis-Menten equation, and I want a reciprocal of this. So let's take 1 over v naught. I just invert the fraction, right? Anybody can do this. It's v naught, and I flipped it over to 1 over v naught. The fraction simply flips over. So instead of having v max times s over km plus s, I have km plus s over v max times s. Simply invert the fraction. Okay, that's not so difficult. So why did they get a Nobel Prize for this? Well, there's more. You have to recognize that that new equation, the thing on the right, the fraction on the right, is simply the sum of two fractions. So this is kind of reverse simplifying, right? We're expanding it. So the thing on the right is the sum of two fractions with the same denominator, right? Remember, when you add fractions, you keep the same denominator and you just add the numerators. So isn't the thing on the right simply Km over that entire denominator plus S over that entire denominator? So they split it up into two fractions, which I'm doing here. So it's Km over Vmax times S plus S over Vmax times S. Well, the last term, the final fraction there, is very simple. We can simplify the S's and just call it 1 over Vmax. That one, very easy. The other thing to realize is the former fraction, right, the Km over Vmax times S, is actually the product of two fractions. Okay, so I know that was a little harder to see, but remember, when you multiply fractions, you multiply numerators and you multiply the denominators. So here, the first fraction there is Km over Vmax times 1 over S. So it's the product of two fractions. And if I write those out separately, it looks like this. So 1 over V naught is Km over Vmax times 1 over S plus the second fraction simplified to 1 over Vmax. Now this looks equally complicated to where we started, but if you look closely and remember which are the variables and which things are constants, remember S and V are variables and Km and Vmax are just constants, they're just numbers, right? This has the equation of a form of a line, right? Y equals mx plus b. Y being a variable, 1 over V naught, yes, it's a reciprocal. I said we're going to have weird axes here, but that's the Y part, equals some constant. Km over Vmax is some constant because it's a fraction of constants. That's m, that's my slope, times x, again we have an inverted axis here, plus some other constant, b. But this tells me a lot. If I plot these with some unusual axes here, right, 1 over V naught, not just V naught, and 1 over S, not just S, I'm going to get a straight line. And the slope of this line is this term here, the m, is Km over Vmax, it's just a constant. And the y-intercept, remember it's y equals mx plus b, the y-intercept is 1 over Vmax. Okay, so I have a line with a slope and an intercept, and everything I want to know about it is in this graph. Okay? So if you do that, it's much simpler to analyze these results than it was with the Michaelis-Menten non-linear curve. Okay? There are some inherent biases to doing it this way, but we won't get into other things like the Eadie-Hofstee plots and things like that. But I want you to learn the basics first. If I do this math, a simple algebra, I can arrive at the Lineweaver-Burk equation. I want you to be able to do that and see that you get the form of a line, y equals mx plus b, and you can graph it as a line. Okay, so this is a linear transformation from a rectangular hyperbola into a straight line. And so we looked at a lot of graphs so far. Let's recap a few of these that we looked at, so pay attention to what you're looking at. Here's 3 graphs that I've shown you so far. If you look at the very top one, it's time and product, right? So product concentration versus time. This is a progression curve. As time proceeds, we make more product. All these lines eventually approach a flat asymptote, and that would be equilibrium. It's where the amount of product doesn't increase anymore. That doesn't mean the reaction has stopped. That means the forward reaction rate is equal to the reverse reaction rate. We covered this last time. That's at equilibrium. Okay, so that's product versus time. The next graph on the left is where I did the Michaelis-Menten plot. Here I'm plotting the velocity, that's all these slopes we got from this first graph, versus the substrate concentration. Each of these S's I used in the first graph. That's each one of these points represents an entire line from the first graph. Here it has the same type of curve, right? It curves over on itself, another asymptote. And where it's approaching is Vmax. So this is not equilibrium at all. This is approaching a point where you're describing the velocity under infinite substrate. That's Vmax. Okay? And half of Vmax, that velocity, occurs at a certain substrate concentration. That substrate concentration is defined as Kl. It's not equal to 1/2 Vmax, don't tell me that, but it's the amount of substrate it takes for the velocity to equal half of maximal. Okay? And if we take this graph and do a linear transformation, we arrive at our straight line, Lineweaver-Burk plot, right? Just like we did on the previous slide. So again, this is 1 over V versus 1 over S. It's showing the same data that this graph shows, but it's a straight line now. So pay attention to what you're looking at when you're looking at a graph. Look at the axes first. What is it describing? Okay, so what are some of these Km values? We said they represent how tight a substrate binds to an enzyme. Right? So here's an example at the top. We had our friend lysozyme we talked about last time, right? The one that punches the holes in the bacterial cell wall or prevents the repair of those holes. And its Km, if you see on the right, is 6 micromolar. Okay, doesn't mean anything to you at this point, it's just a number. Let's compare that to our other friend, carbonic anhydrase, the other enzyme. It has an 8,000 micromolar Km for its substrate CO2. Okay, so which one binds its substrate more tightly? Lysozyme binding the sugar that it binds to, that's the N-hexacetylglucosamine there. So we'll just call it sugar for now. We'll do carbohydrates later. So lysozyme binding its sugar substrate, or carbonic anhydrase binding CO2, its substrate. Which one binds much more tightly?
The lysozyme.
Lysozyme binds its substrate much more tightly, about 1,000-fold tighter, right? Because it's a smaller Km value. Remember, the smaller the Km, the tighter the binding. It's a reciprocal relationship. Okay? But think back to what we said before. Carbonic anhydrase was very fast, right? It did 1 million per second. Whereas lysozyme did one every few seconds. It was exceedingly slow, right? So which one's the better enzyme? Well, I kind of need to take both of those things into account. If you bind very tightly, but you go very fast, that's great, right? You're the best you can be. If you bind very weakly and you go very slow, you're overall a poor enzyme. But what about the combination in reverse? What if you bind very tightly? Lysozyme binds very tightly, a small number, but it's really slow. But carbonic anhydrase was very fast, 1 million per second, but it does not bind very well. So these two, we have to take both categories into account. And we typically do that by doing what's called the catalytic efficiency. We take the speed of the reaction and divide it by the Km value. And the larger that number, the more efficient the enzyme is. So we have to compare both numbers to see which one is the most efficient reaction. Okay? You can win one and lose the other category, but overall you still might be better or worse. The thing I want you to notice also about this chart is the range at which these Kms occur. They have a wide range. Some are in the nanomolar range, which is 1,000 times smaller than the micromolar listed there. And some are 1 million times larger than that in the molar range, which means they don't bind very well at all. So it's a huge range. So why is such a great range? Does this 8,000 mean carbonic anhydrase is a terrible enzyme because it doesn't bind very tightly? No, it makes up for it by going fast. Is lysozyme a great enzyme because it binds so tightly? Not really, because it's very slow. It's very infrequent. So it evolved to be what it is because that fit the scenario the best. Okay? And generally, what happens is the Km value, whatever it might be, and look at the graph down here, here's the Km value, is just above, just larger than this pink box. This pink box represents the physiological concentrations in which that substrate happens to occur. Right? So if it's CO2, the range of CO2 you find in the blood and in the lungs is generally in this range. And the Km value here, 8,000 micromolar or 8 millimolar, is just above that. So the enzyme isn't working in a range where it can vary depending on the concentrations. Right? So it gives the enzyme a certain knowledge of what the concentration around it is. It can detect it by changing its velocity. Right? If you were working in a range well outside of this curve, say up here, the enzyme couldn't adapt to changes in substrate very much. It's a very narrow range. Right? If you were working in a range down here, it would adapt too much and never go fast enough. So it's in this range where it varies quite a bit. The Km is generally just above physiological range. Right? And it evolved to do that. So don't think these numbers are poor or excellent. They are compared to one another, but they are what they are because they're out just above, in general, the physiological range in which that enzyme occurs. Okay. So one more time, let's look at our turnover numbers here. What does this mean? So I have my equations. Sorry about that. I have my equations at the top again. And we're going to lose this k minus 2 term one more time. Right? We're going to say we're going to measure this at the beginning of the reaction where there's no appreciable amount of product around. And let's do some rearrangement here. How fast can this thing go? Well, that would be when all this enzyme is in the ES form. How can I get all the enzyme bound to substrate? Well, let's throw an infinite amount of substrate at it. So there'll be no S left over. All enzyme will be in this form, right? So we're making it a pseudo first order reaction now. So the amount of ES times K2 is the rate of my reaction. Remember, it's the amount of the thing that's there raised to the first power, because there's a coefficient of 1, right? Times the rate constant, K2, gives me the rate of the reaction, V. So I'll write that down. V is K2 times the amount of ES under those conditions. Let's rearrange that a little bit and solve it for V max, because I said the velocity, when I was just describing this, was as fast as it could go. I had an infinite amount of S. Well, that's not just V, that's as fast as it could go. And it's not just the amount of ES present anymore, that's also equal to the total amount of enzyme present, because there'll be none in the free E form. It'll all be bound to S. So I could write ES here, but that's equal just to the amount of enzyme present. It's all in that form. So if I rearrange this a little bit more, right, and solve it for K2, it's just V max divided by ET. So that number is called normalizing it. V max, you remember, I can change. I can make it go faster if I add more enzyme. Remember the students with scissors analogy. If I have more enzyme, I can make it go faster. So I can't compare V maxes from one enzyme to another, but I can compare their K cats, right? So K2 is just how fast it goes under those conditions, or that's the rate, right? But it's the amount of, how fast it can go given a certain amount of enzyme divided by the amount of enzyme I added. It's called normalizing it. If there's more enzyme present, of course it goes faster, but this ratio remains constant. Because remember, adding more enzyme makes it go faster at a linear rate. Go back and look at that slide, it was a straight line. So this K-cat I can compare between enzymes, and that's what we call the turnover number. All right, so that's this number down here. Carbonic anhydrase is about 600,000 per second, and again, lysozyme is about 0.5 per second, or 1 every 2 seconds. So again, very fast, very slow, right? But carbonic anhydrase binds very, very weakly, and lysozyme binds its substrate very tightly. So taken together, you've got to compare the overall specificity. Okay? So this K-cat, or catalytic constant, is a first order rate constant. We know it's a pseudo first order rate constant for the conversion of ES to product, and the enzyme gets recycled. Okay, it's also called the turnover number, the rate limiting step, lots of names for the same thing. We're going to assume this is the limiting step, because K2, again, we're going to eliminate from the equation. So lastly, I had that one question. I was like, which one's the better enzyme? This one's fast, but it binds weakly, and this one was slow, but it binds really tightly. How do we compare the two? I said we'd find something called the catalytic efficiency. I take K-cat, the speed of that reaction, the normalized speed, divide it by Km. Remember, Km is telling me how tightly something binds, but in a reciprocal manner. So if something is fast, K-cat's large. If something binds tightly, Km is small. That's why I'm dividing. So this number overall, if I bind tightly, this gets larger, this gets smaller, which makes the overall number larger. And if I'm fast, this number on top gets bigger, making the overall number also bigger. So if I'm faster or bind tighter, this being smaller, this overall fraction gets larger. So this number determines how well this reaction proceeds. It's catalytic efficiency or specificity. Well, let's see how that works if I change the substrate. If I take an enzyme like chymotrypsin, which is one of our enzymes that cuts proteins peptide bonds, and we said it must cut, like some of the other ones we described, after certain amino acids. Okay? We said trypsin was after a basic amino acid, and we said thrombin occurred after arginines but before glycines, and so forth. You don't have to memorize those, but we had specificity. What if I take chymotrypsin and I'm trying to find out what does it like to cut? And I give it a peptide bond that occurs after a glycine. Okay, glycine's side chain is just H. And I measure its catalytic efficiency, Kcat or Km. I get all the measurements and I get this number, 1.3 times 10 to the minus 1. That's what it is. It's a number. I do it again. This time, instead of putting glycine there, I make sure there's a valine in front of it and ask, is this better? Does it like this substrate better? And I get a number of 2. Well, yeah, that's way better than 1.3 times. This is essentially 0.13, right? So 0.13 to 2. Yeah, that's way better. It's like, 20 times better, roughly. So it prefers to cut after valine. Is that because valine binds more tightly? Or because it can do the catalytic step better? I really don't know. I've taken both into account. I'd have to go back and look at the individual numbers to tell that. But it does prefer valine. So I think, okay, it doesn't like glycine. It likes a bigger group right before where it cuts. But this thing was branched. Does it like branched or not? So let me get a cousin of valine. It's called norvaline. It's not one of our standard amino acids, but it's the same molecular weight as valine. It's an isomer of valine, just called norvaline. And it's just a propyl group, right, instead of this branched isopropyl group. So if I put norvaline there instead of valine, the number goes up to about 36 times 10 to the minus 2, or 3.6 times 10 to the 2. So, which is essentially 360. So this is way better than valine, right? Is it because it fits better? Maybe. Is it because it's faster now? Maybe. I don't know. I have to look at the individual numbers. But it is a better substrate. That's what this says. So I found out it likes to not have a branch point here. That's what this means. But is this long enough? Would it like it if it's longer? So we tried norleucine, which is another isomer of leucine. And it's tenfold better. Almost tenfold better. Yeah, it likes this longer one. Well, let's try something else. Let's make it more bulky out here. So we throw in phenylalanine. We tried lots of things. They tried other ones as well. And you notice we're getting closer and closer to what it actually prefers. Because we're now up to a very large number, right? This is 100,000 compared to we started out less than 1. So we're finding out what it prefers. If you had to keep going, what would you try next? What amino acid would you try after phenylalanine? Noticing this trend that it's getting better.
Tryptophan?
You could try tryptophan, exactly, because it would have this CH2, and then it would be a larger ring structure, right? What's another thing you could try other than tryptophan?
Maybe tyrosine?
I would also try tyrosine, and I don't doubt that they did, right? And if you throw an OH on the end of it here for a tyrosine, or if you make the ring structure bigger, right, with the benzene ring farther out, you don't get as big a number, right? It's not as good as this. In fact, it drops drastically. So clearly they don't show it here because that wasn't the best result. But you would do those experiments, and you're absolutely right at guessing which ones to do next. This is predictive power. You're determining, you learned your amino acids. You try something until it gets better and better and better, and then when it gets worse, you've taken a wrong turn. Let's revise my hypothesis of what it likes and keep going. That's exactly what they do. Okay, let's talk about some representations on how to say how these things work. So we talked about the rates quite a bit, but we haven't talked about mechanisms yet, right? Or how they come together. Okay, so in these reactions, we have more than one substrate involved, and the ones I'm about to describe. Okay, so, and I have a little analogy to help you learn it. So we have two substrates. We can call them A and B. We can call them P and Q. We can call them whatever we like, and then I'll use multiple ones of those. But for the first part, let's start with A and B. Our substrates are A and B, and our products are, let's say, C and D. Okay? So if you imagine an enzyme, A could bind to the enzyme, then B shows up. It's never two at the same time. That's not going to happen. It's one and then the other. You don't have three bodies coming together at once. So you have your enzyme and A binds. Then you have an E-A complex, right? We're not going to say S anymore because we have more than one S. We can't just randomly say S. So we have an E binding to A. We have an E-A complex. Then B comes along and binds. We now have an E-A-B complex. And that allows the chemistry to take place. All the stuff's there. We do our chemistry. A and B turn into C and D. And then one of those leaves, let's say D leaves, leaving behind an EC complex, and then C leaves. And I'm back to my free enzyme, and I can do the reaction again. Okay? What I just described was an ordered sequential mechanism. Okay? And that's shown in the middle of the screen here. And this on the right is called a Cleland diagram, named after Moe is what everybody called him, but William Wallace Cleland, who came up with all this stuff. And it starts out with drawing a line, just a horizontal line, writing E on each end, because we start and end with free enzyme. And we represent events along the way. This is not necessarily time, but it's as the reaction progresses, these events happen. So A binds, see the arrow going down to the line. E binds to A, we get EA. B binds next, we get an EAB complex. Both substrates are on the enzyme. We have some chemistry take place, and we get ECD. D leaves, and then C leaves, and we're back to enzyme. Okay, very simple. An alternative to that is what's called random sequential at the top. It's still called sequential because sequential means everybody has to be on the enzyme for the reaction to take place. And you notice that's still true. EAB must still be formed for the reaction to take place. All the substrates must be there. That's what sequential means. Ordered means A binds before B, whatever A and B might be. Random means it's okay whichever one binds first. I'm fine with that. A could bind first, make it an EA complex, then B to get to EAB. Or B could bind first and make an EB complex, then A shows up, and I still arrive at EAB. It's random which one binds. There's really no preference. That's what we're saying by random. Whereas ordered means in no way will B ever bind without A already there. That's what this is saying. So there's an order to our substrates. A binds, then B. B will never bind to E. Never find an EB complex in this scenario. A must be there first. B does not bind unless A is there. We did an example of that with our hexokinase. I said ATP bound, and when it did, it clamped down on it. Remember, it changed shape, making the pocket for the glucose. The glucose will not bind to it unless ATP binds first. So that's an example of ordered sequential. There are other examples where whichever substrate shows up first binds first. That's random sequential. Those two should make sense. Okay? There is one other one. It's called double displacement, or in Cleland's terms, he called it ping pong because it looks like two half reactions taking place. And he had some more nomenclature for it depending on the number of substrates and number of products. In this case, we have two substrates. I'm not using A and B anymore because I like my letters better, and hopefully you agree with me here. My substrates are going to be Q and P, and my products are O and R, right? So I have two substrates, Q and P, and two products, O and R. Cleland would have called this a bi ping pong. The first bi indicating there are two substrates, and the second bi indicating there are two products. That's not true for every reaction, but in this example, it would be called a bi ping pong reaction, or double displacement. Double indicating there's two separate reactions taking place. Okay, so let's look at what's happening. We have our enzyme again. Draw our line. We end up with the same enzyme when we're done. Otherwise, it wouldn't be an enzyme. Not worse for wear in the process. So the first substrate binds Q, and it forms an EQ complex, kind of like AB. Kind of like EA we had before. Then something happens. When the first substrate is there, the second substrate has yet to show up. It's nowhere around. Just the first substrate binding triggers a reaction to take place. And what happens is Q gets split into two parts. One part of itself leaves as the O, and you see why I chose these letters. Part of itself stays left behind, covalently attached to the enzyme. This is unusual for enzymes, right? We don't usually have a substrate covalently bound. Here we do. So here we have first substrate binding forming an ES complex or EQ complex. I'm going to label it Q. Some chemistry takes place where part of this molecule leaves and part of it is left behind. Now you see why I chose the letter. Then the second substrate shows up, right? We get an E/P complex, and it picks up the very piece that was left behind to become R. So we get an ER complex, and then the product R leaves, leaving E ready to do this again. But we must do the first half reaction followed by the second half reaction. This middle piece, this modified enzyme intermediate, can't bind another Q yet. It must finish this other reaction. Right? So we have to do the ping, then the pong, before we can do another ping, is why we said it. Okay? So this is a double displacement. But I must be able to isolate this intermediate. How would you do this type of experiment? Because there's no way I can isolate EAB. It would turn into product right away. How could I isolate this E/intermediate? Can you think of a way to have it occur and trap it? And that would prove double displacement.
You can do it in an environment that doesn't have any P.
Exactly. You give it the first substrate, Q, but not P. And of course it does the first reaction until it runs out of Q. It makes a lot of O in the process, and all the enzymes will eventually be turned into E/ and the reaction will stop. Now if you give it P, it'll continue. So you do the first part like you suggested in the absence of P, and I'll detect this modified enzyme intermediate and lots of O around. But it'll never make R. Then you add P, and it turns it into R. So I know it's functional still, but I could collect the intermediate enzyme. There is no way to do that up here. If I give the enzyme just A or just B, nothing happens. I have to give it A and B before I get any products. So seeing a product where you give it one of the two confirms that it's a double displacement reaction. Now, if you didn't know which one bound first, Q or P, and you give it P, of course nothing happens. You have to try both. Okay, so I have a little analogy for this. It's not as elaborate as the other one we did, but I think it's funnier. So imagine this reaction taking place it's a drug deal happening on a bus. Right? I like colorful analogies to help you remember it. Right? I'm not into drugs or anything, but I like outrageous analogies because they stick in your mind. So imagine this being a drug deal on a bus. Right? So the two people exchanging money and goods, whatever they might be, right? And if you don't like it being a drug deal, you could be selling Girl Scout cookies or something, whatever you'd like to put in its place. So that's the two substrates. Okay, so A and B, for instance, or Q and P. Okay, so in the ordered sequential one, the first one I described, E is the bus, right? So substrate A or person A gets on the bus, right? Takes their seat. Now they take a window seat on the bus because it's an ordered addition. They can only sit where they're assigned. They sit in the window seat. And then person B gets on and sits in the aisle seat next to A. Of course, if B were to try to get on first, that seat's not available yet. You have to sit by the window first, right? It's kind of like makes sense when you get on planes. You want to fill in the ones by the window first. Doesn't always happen in reality, but here it will with enzymes. Right? So A must get on the bus first, take their seat. B gets on, sits in the aisle seat next to A. They do their exchange, right? And then D, which is now the modified version of A, perhaps, or either they are missing their cookies and have the money, or missing their money and have the cookies now, or whatever it might be. They get off the bus. Of course, they're sitting in the aisle seat, gets off first. Then EC is the bus with the person in the window seat, and then they get off. And then the bus is able to do this reaction again and again and again. Okay? In random sequential, both individuals take aisle seats. Either one could take their seat first, but they're sitting across from each other in the aisle. So A can sit by their seat, B can sit in their seat. One doesn't preclude the other from sitting in their seat like we just talked about for ordered. And either one could sit first, then the other. They do their exchange, and then they either can get off first or second. Okay, the bus is no worse for the wear. Okay? In double displacement, it's more subtle. Right? So here, person Q gets on the bus with a briefcase. Okay? So person Q gets on the bus. We have a bus now with you holding a briefcase. You get off the bus, that's O, leaving your briefcase behind, the little slash. Okay? You are totally gone. The second person never meets you. This is one of those more secretive exchanges, right? So substrate P now gets on the bus, sits down next to your briefcase you left, picks it up, and leaves with your briefcase. In this case, Q and P, the substrates, never meet. They never see each other, right? So that's my little analogy for how you can tell ordered. They sit in their ordered seats, right? Assigned seats. From random, they could sit next to each other. Doesn't matter who gets on first. Versus double displacement, the more secretive, leaving the briefcase on the bus type of exchange. Okay, so hopefully those three will help you tell those type of mechanisms apart. Okay. Right, and then we want to go on to what's called allosteric enzymes. Okay, so allosteric enzymes have a meaning. The word allosteric literally means alternative place, right? Allo meaning alternative or other. Steric meaning a position, place, a space, a volume. It's something. It's a place that needs to take place. So allosteric literally means other than the active site, right? It's an enzyme that is being modified, being told to work faster, to slow down, to turn on, to turn off, whatever it might be, by something binding to it elsewhere, other than the active site. Okay? That's what allosteric means. Don't confuse that with anything else. That's all allosteric means. So you could have another small molecule show up and modify the enzyme. It could be a covalent attachment, like we put a methyl group on it somewhere, not in the active site, but somewhere else. We could put let's try, not histone because it wasn't really an enzyme, but other enzymes where you put a methyl group on it or an acetate group on it, or you protonate it or deprotonate it, or a GTP or an ATP attaches a phosphate to it. Any of those type of modifications. Or some other small molecule just binds without a covalent bond, right? Like your repressors and your inducers we talked about earlier. They bind to some enzyme, turning it on or off, or tweaking it faster or slower. All those are allosteric controls. Okay? Many enzymes are controlled allosterically. Okay? And most of them are completely reversible. When we put the molecule on, it might speed up or slow down. We could also take it away to reverse those effects. Right? It could be covalent, could be non-covalent. But all this means is we're going to modify the enzyme's activity by something else attaching to it or binding to it at a site distant from the active site. Okay? Most of these enzymes that act this way are the first committed step in a metabolic pathway. And we're going to cover metabolism in the next block. But if you have a pathway, a series of enzymes that turns one substrate into a bunch of other molecules and finally at a product at the end, series of enzymes, and it's a committed pathway, I want to control whether I do that pathway at generally the first irreversible step. And that enzyme is most often controlled allosterically. Okay, we'll look at a lot of examples when we get to metabolism. I just want you to understand the definitions now. Okay? Allosterically regulated enzymes like this don't have your normal Michaelis-Menten curve. Right? So if you look at this, we have substrate concentration on the bottom and reaction velocity on the y-axis again. So just like before, this is a V versus S graph. It normally has that rectangular hyperbola shape. This one does not. It has this S shape to it, right? Or called a hyperbolic shape, right? It's not a rectangular hyperbola anymore, right? It's sigmoidal, right? S shaped, no longer a hyperbola. If you see this type of S shape, it's probably an allosterically controlled enzyme. So clearly our equation doesn't fit, right? It doesn't have the V equals V max times S over Km plus S anymore. Those S's are now going to have non-1 exponents, right? We're not going to cover it in this class because we don't have time to cover all those, but they'll have exponents that are no longer 1. So it's no longer a simple equation anymore. You can't just take the reciprocal and get a straight line anymore. Okay? But a lot of misconceptions surround this allosteric thing. Textbooks will tell you that allosteric equals non-competitive inhibition. That is not true. We'll talk about inhibition on our next lecture, but allosteric inhibition does not equate to non-competitive. That is not a true statement. Okay, so don't believe that. Sigmoidal shapes here in the graph generally mean allosteric control. Okay? If it's got a normal hyperbolic shape, then it's generally not allosterically controlled, or not at that moment. Okay? One example of that here, if I have a normal blue curve here, right, not bound to any kind of inhibitor, right, it's got a normal hyperbolic shape. If I add an inhibitor, an allosteric inhibitor, this has nothing to do with competitive or uncompetitive or non-competitive. We'll talk about those next time. This is just an allosteric inhibitor. It binds somewhere else. It can change the shape. So it makes the blue curve look more like the black curve. And if I add even more, it could look like the red curve. And alternatively, if I have a normal allosteric one, like the black curve, and I add some activator to make it work better, it can turn into the blue shape and that behave more like Michaelis-Menten kinetics. This is how a lot of your enzymes behave, right? So they'll have small molecules that adjust their behavior depending on their presence. And you notice what it's doing, it doesn't change Vmax at all. These all three still approach the same asymptote as s goes to infinity. And they all still have a velocity near zero as s goes to zero. But they change where the Km appears to be. It's called the apparent Km. Km has an apparent shift, which means for the same velocity occurs at different substrate concentrations, right? So this modulation is so you can conserve substrate or use it faster and get the same result depending on the conditions, right? Lots of enzymes work this way, particularly those ones at the committed steps.